Hi, welcome back. John Valvano here. In today's lecture, we're going to talk about digital logic, and in particular, we're going to look at voltage and current. And these are important parameters when we think of interfacing. We're going to go further and use a bipolar junction transistor to interface a speaker so that we can make sound. And throughout this whole discussion, this issue of capacitance will be an important parameter, and we're going to watch for it as we go along. All right, let's first talk about voltage and current as it applies to digital interfacing. And so in this diagram here, we're considering what happens when the output is high. Okay? When the output is high, we have a p-channel MOS transistor right here, which is on and driving current in this direction. And that current goes from the output to the input and is used to drive the gate of these n-channel transistors. So we see when the output is high, current flows out of this gate and into those. And the amount of current that it can supply is a function of this p-channel MOS transistor, and the amount of current that it requires will be a function of these. And we'll see that this current here will have a maximum of about 2 milliamps in normal mode, but we'll only need about 2 microamps of current to drive its inputs. So the voltage when the output is high is called VOH, and the maximum current that it can deliver, in this case 2 milliamps, is called IOH. And the amount of current it requires to drive the input is called IIH. And these are important to balance when the output is high. We see a similar situation when the output wants to be low, except current's going to go in the other direction. Let's see how that happens. To make this output low, we're going to drive and turn on the N channel here at the output. And that will allow current to sink to ground through this output. But where does the current come from? Obviously, it comes from the inputs. And so the p-channel MOSFETs at the input are going to require current at their gates in order to turn on. So the current, while the output is low, comes from the supply of the input through the gate, across the interface and down to ground. Okay? And again, the current when the output is low, this maximum current is called IOH, and it's about 2 milliamps for our device. And the developed voltage when the output is low is called VOH. Okay? The IIL, because it's a CMOS logic, is going to be the same 2 microamps for each device. So in summary for this, we see that when the output is low, current flows actually from the input down to the output. All right. When we interface various logic families together, we have to consider this voltage current parameters in order to make sure it works. And so as we can make up systems, we're interested in what is the supply voltage for that device. And most of the objects that we will use in this class are going to have a 3.3 volt logic. Now there may be some 5, and it turns out the processor itself uses some 1.5 volt logic, but most of the stuff we will use in this class is 3 volt logic, 3.3. The amount of current it requires to run is important, and when we want low power interfaces, we want low power devices, how fast it works, and just as a heads up, the speed is going to be a function of capacitance, and we'll see this over and over again. When we decide to choose a family, we're interested in how much current it can drive at its outputs and how much current it requires at its inputs. All right, so in order to see if it's going to work, let's first look at voltage. Again, if you look at the output of one device connected to the input of another device, we can define what is the smallest voltage that the output will be if it is high, okay? And that's VOH. And what's the largest voltage the output could be if the output is low? That's VOL, okay? Assuming the current is not overloaded. And then at the input, we're interested in what voltage range does the input consider low. That's VIL. And for obvious reasons, the output has to be lower than the input requires. If this inequality is true, whenever the output drives a low, the input will see it as a low. We have a similar situation when the output is high. The VIH is the range, the smallest input voltage that the input considers a high. And so if the output drives higher than that, then it works. So again, we have two inequalities associated with voltage. And does this output properly drive a high and recognized by a high? That's this. And does this output drive a low, and is it recognized as a low? That's that. Okay. If we look at a bunch of different families, we can see all this together. Like I said, we have TM4C123, and the output low currents are about 2 milliamps. If we want to have more, there's a 4 milliamp mode and an 8 milliamp mode, but for most of our interfaces, we won't change that. And so the maximum current that the output can source when it's high will be 2 milliamps. And the maximum current that the output can sink down to ground will also be 2 milliamps. There are some microcontrollers that can source and sink more current, but ours is either 2, 4, or 8, depending on how we connect it. And we can see the different current driving capabilities for the various types of transistor logic. Again, we have CMOS transistor logic, so it's complementary. So the high and low work in a very similar manner. All right, let's look at it in a little more detail. Okay, and let's look at both voltage and current this time. Again, we're gonna look at what happens when the output is trying to drive a high. And as we saw last time, the P-channel transistor here is active when the output is high, and the current is going to flow in this direction. That's what we saw last time. But now let's look at how the currents add up. What happens as I connect more and more inputs to my output? Okay? And we saw that for our device, the maximum current that I can source was 2 milliamps when the output is high. That's IOH. But what happens is, as I try to source more and more current, the actual voltage is going to drop. And so this parameter VOH and IOH is actually just an operating point that we actually never reach. And that is, at what point does the output stop working? And so as the current gets larger, the voltage will drop somewhere between 3.3 down to 2.4 volts. Okay. All right. And as we saw last time, as we added up inputs, the current when the input is high, in our case, it's about 2 microamps, is the amount of current that it will actually need to work. And so, as you can see, is if we tie one TM4C 123 to another TM4C 123. This 2 microamp current here needed is going to put us way over here on the operating point. All right, that's when it's high. And so in order for it to work, we need the output voltage higher than the required input voltage, and we need the ability to source the current to be larger than the current needed for the inputs. Okay? And again, the actual operating point of current is going to be determined here by the currents that the input used, and not by the maximum current that this thing generates. We have a similar sort of situation when we're driving it low, and again, to drive it low, we'll turn on this N channel, and that N channel will actually activate all the P channels in the input, and so the current, when the output is low, it's going to flow in this direction. And so, just like before, this 2 milliamps here represents this IOL is the maximum current, such that the voltage here will be less than a certain parameter. Okay? And the actual current is going to be determined by the inputs, and if this is a 2 microamp CMOS device, we're going to be operating way down here. Okay? And so as the current for your inputs increases, the voltage will increase. So VOL doesn't tell you the actual voltage at the output, but it gives you the maximum voltage that output could be given the maximum current. And so we're going to operate somewhere in this range for our devices. So the device has to be able to drive all that current, and this voltage must be less. So those are the two inequalities for the output. If we see all those inequalities together in one design parameter, this will be our design specification for connecting up two digital circuits to make sure they work. Now, we haven't told you how fast it's going to go yet, but this is just in a static sense, well, it will work. And here the voltage is shown. Again, the VOH of our device is 2.4 volts, and we saw that as the current goes from 0 to 2 milliamps, the output's going to be in that range. And the VOL for our device is 0.4 volts. And again, as the current goes from 0 to 2 milliamps, that voltage will go from 0 to 0.4 volts. And that's for our CMOS 3-volt microprocessor. Let's talk about interfacing. Previously we were talking about hooking one digital device up to another device. So now let's hook up an output to something that's not digital. We want to drive a speaker, for instance. And this is a little bit scary. This is sort of how the bipolar junction transistor works. But in this class, we're not going to drive it in linear mode. We're going to either turn it off, okay? We're going to drive this in two modes, off. This emitter here is going to be ground. And so to turn this off, we're going to give it a 0 volts here, and that will turn off this transistor. Okay, so no worries there. The second mode we're going to use is called saturation. And in saturation mode, what we're going to do is make this voltage here big enough, somewhere between 0.6 to 1.2 volts, depending on the transistor. We're going to make this voltage big enough to drive this completely into saturation. In other words, once I'm in saturation, what I'm going to have is this voltage when across the collector emitter is going to drive down to, say, 0.3 volts. So and current's going to flow this way. Right? So we're going to be in two modes, either off, in which case no current flows, or we're going to be completely on, in which case this current is going to be at up to maximum, but the voltage across the collector to emitter will essentially go to 0. So it's essentially a digitally controlled switch. And the way we're going to use it here is to connect it up to a speaker. And we'll talk about this resistor in a moment. But just let's review the saturated mode circuit. So there's our speaker. And here's our power supply. And we're actually going to put in a square wave here. Okay, so this digital signal right there is going to be a square wave. And so let's analyze this from the two modes that we talked about. All right? The first mode was off mode. That's an easy one. When the input is a low, when that's 0 volts, there is no voltage, no VBE, across this transistor, in which case it will be off. And off means off. Off means that this current will be 0. And that means the power to the speaker will be 0. So we've delivered no power to this speaker when it's off. Okay? The second mode is on. So if the input is 3.3 volts, so let's look at this. And there's the speaker. That's going to be a 32 ohm headphone speaker, 3.3 volts. Okay. So when this is on, saturated mode, completely on, this voltage when the collector emitter, this VCE voltage, is going to be about 0.3 volts. Okay? And in order to get it to come on, if this is a PN2222 bipolar junction transistor, there's lots of transistors you could use, but we're going to use that one, that we're going to need about 1.2 volts across here. Okay, so we'll talk about the resistor in a moment, but just for you to get a sense of what happens. And so now let's look at this is saturated mode. This is completely on. This is on mode, saturated mode. And so in saturated mode, we can see that the current here, okay, the current is going to be large. And we can use Ohm's law to find it out, right? We look at Ohm's law, we see 3.3 volts minus 0.3 volts over 32 ohms. And we can see that this is about 100 milliamps. Okay? Now you can see why we didn't hook it up to the microcontroller, right? Because you remember of the microcontroller, the IOH and IOL of the microcontroller was only 2 milliamps. And even in 8 milliamp mode, there was nowhere near the 100 milliamps needed to fully energize this speaker. And so we can see that the interface was required, and we're using a saturated mode BJT to do that interface. All right. Here's some transistors. Let's talk about some parameters that we can use to select a transistor. Like I said, I'm going to use a PN2222. This is a bipolar junction transistor. It's an NPN, like I drew. Later in the course, when we get to the motors, we're going to use another transistor called a Darlington. We're going to use the tip 120, which is also an NPN. But as we can see, the difference between a BJT and a Darlington is the amount of current that output can drive, because this one has to drive the motor, and this one's just driving headphone speakers. The collector current specification tells you what's the maximum current that this transistor can generate before it breaks down. And we can see that this 150 is bigger than the 100 we estimated before, and so it will operate. One of the interesting parameters associated, we've talked about the VBE, that's the saturation voltage, and so if the base emitter voltage goes above 1.2 volts, that thing goes into saturation. And at saturation, the output voltage, the collector emitter voltage, in our case is going to be 0.3 volts. Another parameter, and this will help us choose the resistor that I left off in the last one, is called the current gain. And this current gain is, if we look at the collector current, we can think of this as a current amplifier that takes the base current, which is the current coming out of the microcontroller. Remember, the base current is essentially IOH. It's the output high current of the microcontroller, and then amplifies it to create the collector current. And this 100 gain for the 2222 is an important design parameter. And we can see the reason why we chose the Darlington is we can drive a lot more current out with a lot smaller current in, because the Darlington has a 10 times current gain. But it's a much bigger chip, way too big for us. All right, so let's talk about the interfacing of the speaker itself, and let's focus in on how to get that resistor value. Okay, so I'm going to play a little loose with the numbers, and I promise you in advance that I'm loose, but bear with me. Okay, so let's first the off mode is easy. 0 goes to 0. Okay, so we don't have to do any thinking. 0 volts out of the microcontroller is going to turn it completely off, such that there is there's no current, no collector current. So let's talk about on mode. All right, let's talk about on mode. In on mode, the output of the microcontroller we saw before was going to be a number between 2.4 volts to 3.3 volts, depending on the current. So I'll leave that off for now, but let's just call it V out. It's in that range because the output is going to be high. All right, and that goes across the resistor, which I want to determine its value, into the base of the BJT. and the collector is tied to the 32 ohm speaker to 3.3 volts. Okay, that was the circuit we drew over and over again. And you remembered that in order to turn it completely on, full bore on, we're going to have about 100 milliamps of current right here, right? Full bore on. And we're going to have a voltage drop across here of about 0.3 volts. And so we saw before, and we needed a 1.2 volt base voltage across here, okay? And so we can now use the current gain of this amplifier. This is the collector current, because there's the collector, that's the current going into the collector. And now we can look at the base current. Okay, which is the collector current divided by 100. So the base current here is going to be about 1 milliamp. See that? See that? That's how this thing works. So a 1 milliamp current here is going to be amplified to a 100 milliamp current there. Okay? And now, though, is that 1 milliamp scary? No, because you remember that IOH is 2 milliamps, or 4, or 8. Okay, so we can clearly be able to drive a 1 milliamp base current in order to get 100 milliamps to go through my speaker. Okay? And now I can do Ohm's law to find R. You see that? I got to now, if I were to drive 1 milliamp into this device, what voltage would it be? I didn't bring my calculator, so I'm going to choose a number that's easy to calculate. So go ahead and get out your voltmeter and see what it really is. But in order to make my math easy for my old mind, I'm going to use 3.2 volts. Okay? And I know that the base emitter voltage will rise itself up to 1.2 volts. And now I can see I got a 2 volt drop across that resistor, and I got a 1 milliamp current. So I got a 2 volt, and I want to have 1 milliamp of current, and I'm going to use that in Ohm's law to say that if I have a resistor of 2K, that will drive this transistor completely into saturation. Okay? Now I do the caveat. I lied to you. Everything is not the way I said it, and let's look at all the things that aren't the same. Okay? First of all, VCE, may actually be less than 0.3 volts. That was the maximum. So it actually might be less. So that's not right. Okay? So this current, we're not sure of it either, but it's about 100 milliamps. All right. This voltage is not exactly 1.2 volts. Get out your voltmeter and measure it. It's probably less than that, actually. But we don't know what it is. This voltage here, I already told you I guessed on that one. This current gain, where'd it go? It's an approximation. It's maybe less. Okay, so all of these are approximations, which says that once I get out all these things, I'm going to do one of two things. I'm going to take this resistance 2K and say, well, if I want it to go into saturation, I'm going to put more current. I'm going to put more current into it. So I'm going to actually use either a 1K or a 470 ohm and put in 2 or 4 times the amount of current that I think I need to fully drive it into saturation. Okay? And then I'm going to have to set this up in 4 milliamp mode or 8 milliamp mode to run. It turns out this is lab 3. Nobody wants to wake up the dead, and so we're actually want to drive it not completely into saturation. And so if I take this resistor and go the other direction, if I go to 4.7K or if I go to 10K, it's actually going to be softer, quieter, nicer, more pleasant to the other people in the room. And so this is what my recommendation here is for lab 3. To make the alarm clock sound, we're actually going to make this resistor bigger than what it would take to go into saturation so that the speaker isn't too loud. Okay? Let's look at the power, because that's interesting. In full bore mode, I can see that the power here is going to be, we calculated this earlier, 3 volts squared divided by 32 ohms, or we could do 3 volts times 0.1 amp, and we can see that we're going to be driving about 0.3 watts. So that's sort of the energy, that's the power delivered to the speaker in an oscillatory way in the square wave. And that's pretty loud, actually. So we're going to want to choose a resistor smaller than 2K so that it doesn't become too loud. All right. There's the details that I went through. Okay. Let's talk about capacitance. Capacitance is either totally wonderful or completely bad, depending upon whether you're digital, in which case it's bad, or you're analog, in which case it's good. But as it turns out, we saw that the output current of a device was about 2 milliamps and the input current was about 2 microamps. That does not mean you can connect 1,000 inputs to your output. That actually won't work. And that is because the parameter that decides how fast it runs is going to be the capacitive load at the input. And this is a significant part of CMOS logic, such that this input capacitance or the capacitance that might exist in the cable is going to determine how fast it rises. And so the output impedance, if you like, of that transistor multiplied times the input capacitance of this input device is going to determine the slew rate, right? The time constant here of R times C. And as this capacitance gets large, either by having multiple inputs or having inputs connected by a long cable, we're going to have to slow this down. And if we look at the RC step response, this is going to be on the test, by the way. If we put in a step voltage here at this input, we will see an exponential response. When I add the step input or I remove the step, we're going to see an exponential response. And that time constant is going to be this R times that C. And those are the parameters that will determine how fast this is. And so if you want to go faster, you can sort of think of ways to do it. We're going to decrease R, which means we're going to have more current. And we're going to more current and more power. Or we could figure out better technology, better cabling or whatever to reduce that capacitance. Okay, so again, for a digital circuit, this capacitance here will affect how fast it runs. In the analog circuit, the capacitance removes noise. And we can sort of see that here. And it turns out this slew rate here, this voltage, this dV dt at the digital circuit is the thing that's going to generate electromagnetic fields. So this changing voltage, this changing current is what's going to generate the radiation. The radiation noise from this line is going to propagate to whatever's next to it. And so sometimes in digital circuits, if we want to reduce the noise, we're going to reduce the speed and reduce the slew rate of these inputs so that we don't radiate a lot of noise. So capacitance will be a big thing this semester. It makes things go slow, but it also makes noise go away. So be careful. It's both good and bad. All right. So in summary, watch the R, L's, and C's. We didn't talk about L today, but we'll do that more when we get to our motors. Today we talked about resistance and capacitance. These are important parameters when we do interfacing. Remember that the voltages is one set of inequalities and current is the other set. There's really no way to get around the fact if you want to go fast, it generally takes power. Okay, either more voltage, more current. And so there is this natural relationship between the execution speed of a digital system and the electrical power used to run it. All right, next we're going to talk about specifications, design processes, the requirements document, all of which is important as we design things. See you next time.